Hey guys, so for my section I had more examples of polymers, specifically natural and synthetic rubbers, which was chapter 16, section 5, but basically just gave a little bit of real-world examples on how polymer reactions occur in real life. So it started with showing that rubbers can be created naturally, typically through the biosynthesis of plants, when you have an isoprene that polymerizes to a cis-1,4 polyisoprene, which is just a rubber. And this happens because identical monomers of isoprene undergo like a nucleophilic attack and attach to each other in a identical pattern that repeats itself through the first and fourth carbons. Those would be your attachment points with the other monomers. And then scientists try to replicate this same natural rubber in lab and have come pretty close. They only have to use catalysts favoring this cis polymer in order to achieve a natural type rubber. But in lab, scientists are typically just creating synthetic rubbers. So one example is chloroprene undergoing a free radical polymerization to create neoprene, which is a common rubber that is used as insulation for electrical wiring, fan belts for cars, and even in scuba diving wetsuits. So following the same carbon-1, carbon-4 connection process to create neoprene, you have a trans molecule named 1,4-polychloroprene, and it also will occur in this repeating type of pattern. Moving on, it touched a little bit on how elasticity works, and so some polymers are also called elastomers, meaning that when they are stretched or some force is put onto it, the chains will slide back and forth against like the neighboring polymer chains, and then if you were to release that pressure, the chains would snap back into their original positions and shape. And so this occurs with many polymers, but only in like specific temperatures. So in lab, if you wanted to create a polymer that you did want to have elasticity, you would use this method called vulcanization. And here, you can, if you add sulfurs to when you're polymerizing, even at high temperatures, you'll have an increased elasticity because the disulfide links will help the chains move back and forth instead of possibly just keeping them more rigid in their structure under these differing temperatures. And so then one more example the book gave was this styrene butadiene rubber, or SBR, and this is the most used rubber or polymer in the United States because it is typically used in any kind of car or automobile tire. And it's prepared with a free radical polymerization of styrene and 1,3-butadiene. As Natalie kind of talked about before, this is going to be a copolymer just because it is made of two very different monomers, but you can see how they link down here. Using the same nucleophilic attack method, and it will create a repeating pattern like we saw before. Okay, so now for some examples. This is the one problem the book gave about this section, but basically it's just showing some polymers, and it's asking what monomer or identical monomers could be used to create each of these structures. And so you should note that both of these polymers are going to be synthetically made in the lab due to the fact that they are in trans conformation, but that doesn't make too much of an impact on the answer. Here's what they will look like, and you can kind of deduce these structures because you know that you need two double bonds in conjugation with each other to create a polymer with the repeating pattern, and because you need some way for the monomers to connect to each other. And so, like for example, this would make sense because you used to have a double bond here, but that was if you gone backwards and had added this one as a nucleophilic attack and moved this one over the neutralize the charge, this would be the structure you would have started with. So going back, you can see this here, it would be your double bond here and here instead of here. And then you would cut the molecule right through here and right through here. Same thing applies with B, except you have substituents on both sides of this double bond, but same thing applies. You're just going to have a double bond here and here, which eventually when connecting to create the full polymer, move to connect here and then move to neutralize here. And same thing, you would cut the monomer out right there to give you this structure. So that's about it. If you have any questions, let me know.